Now let's move back to this question. We'll be referring this to as f of s and this as g of s. We need to find the f of t and g of t, so we'll be taking the Laplace inverse of f of s individually and g of s individually. Let's do that. Now that we have found the f of t, which is sine of at divided by a, and g of t, which is cos of at, I'll be substituting f of t here and g of t here. Now comparing it with the convolution theorem, this f of t is this one, and this g of t is this one. When we'll be writing it in form of integral, we'll be replacing the t from f of t with t minus u. So we're going to be replacing this with t minus u. And similarly, for g of t, we'll be replacing t by u and write the integral in this form. Let's rewrite this. Now we'll be opening the round bracket inside the sine function, so it becomes sine at minus au, which matches the form sine a minus b. And we know its trigonometric identity is equal to sine a cos b minus cos a sine b. So let's do that directly here. Now you can see that we're integrating with respect to u. So we'll be taking this out of the integral and this out of the integral. So let's rewrite this. Now we recall the identity of cos 2 theta. We know that cos 2 theta is equal to 2 cos squared theta minus 1. So let's make this the subject, which means that cos squared theta is equal to cos 2 theta plus 1 divided by 2, which we'll be substituting it here because we do not know any such direct method of integrating a cos square. And for this one, we know that sine 2 theta is equal to 2 sine theta cos theta. Let's make sine theta cos theta the subject, so it becomes Now we'll be substituting sine 2 theta divided by 2 here and carry out its integration as well. Let's continue. We can see that the value of theta is a of u. So instead of writing theta, I'll be writing 2au here. And instead of writing sine 2 theta, I'll be writing sine 2au. Now, we know that the integration of cos 2au goes like this. This is the operator. Introducing 2 here and outside the integral. Eventually giving us 1 by 2 sine 2au. This becomes u. The integration of sine is like this. This will be leaving us with the minus cos 2au divided by 2. So let's complete these steps. Now let's apply the upper and the lower limits. When we'll be applying the lower limit over this, it becomes 0. And similarly, when we'll be applying the lower limit here, it becomes 0. However, for this one, when we'll be applying the lower limit, it becomes minus 1 divided by 2. Let's apply the limits. We are going to expand the brackets. You can see that the denominator 4a is common here, here, and here. So we can rewrite it as one individual term. If you observe the numerator closely, you can see that this matches the form sine of a sine of b plus cos of A, cos of B, which is a trigonometric identity for cos of A minus B. A is equal to 80 and B is equal to 280. So A minus B would mean 80 minus 280. That is equal to minus 80. Substituting it in the cos, this will be giving us cos minus 80. We know cos of negative theta is equal to just cos of theta, because according to ASTC quadrants, the negative theta is going to be found in the fourth quadrant where cos is positive. Just write cos of 80 instead of this. You can notice that this cos of 80 and this cos of 80 are going to cancel out, leaving numerator with 0. So this entire term becomes 0, giving us this as the final answer. You're going to solve this expression and find its inverse Laplace transform. We can clearly see that this expression can be represented as a product of two simpler parts, 1 divided by s plus a and s divided by s squared plus 1. We can find the inverse Laplace transform of each of these terms individually. So I'll be representing this as f of s and this as g of s. And apply the convolution theorem instead. So finding the value of f of t and g of t, by finding the Laplace inverse of f of s and g of s, we would get this. Now, as per the convolution theorem, the f of t, asterisk, g of t was written further as the integral from 0 to t, f of t minus u, g of u. So I'll be replacing this t here with t minus u, and this t here with u. So let's rewrite this. Expanding the brackets here. Since we are integrating with respect to u, we will be taking e power minus at out of the integral. Now let's solve this using the tabular integration right here. I'll be differentiating here with respect to u, and here I'll be integrating with respect to u. Since we are integrating with respect to u, we can take a squared out of this integral sign here. And then you'll be taking it towards the left-hand side of the equation. So you'll get this. Now, we can eventually find the integration of e power au cos of u by taking this towards the right-hand side over here. So let's substitute this at the place of when applying the lower limit, we know that this sine of u becomes sine of 0, so this entire term becomes 0. And when applying the lower limit here, this cos of u becomes cos of 0, which becomes 1 here. So let's apply the limits and write for a final answer. When expanding the brackets, the e power minus 80 and e power 80 cancel out. And similarly for this term, e power minus 80 and e power 80 is going to cancel out. So let's write our final answer. This is going to be our final answer.